Have you ever stopped to think about what a planet spinning in orbit, a baseball flying through the air, and a high-tech robotic arm could possibly have in common? Well, it turns out they all play by the exact same rulebook, classical mechanics. And we're about to unpack the fundamental principles that govern literally everything that moves. Let's get right into it.
So seriously, what is the connection? I know, it sounds totally random, right? But the answer is this single, beautiful set of rules. Everything you're looking at here is governed by the universal principles of motion, force, and energy. And by the time we're done, you're going to start seeing our entire world through that very same lens.
So here's our game plan. We're going to start with the basic lingo, how we even talk about motion. Then we'll get into the laws that actually cause it. After that, we'll look at some real-world forces we all deal with, dive into the physics of energy, and finally, see how we can use all this cool knowledge to our advantage.
First up, kinematics. Okay, just think of this as the geometry of motion. It's all about describing how things move, their paths, their speeds, their acceleration. Right now, we're not getting bogged down with why they're moving. We're just being good observers, just measuring what we see. Let's break this down with a super simple example. Picture this. You get up from your chair, you walk a perfect circle around the room, and you sit right back down. The distance you traveled is the actual length of that circle you walked. But your displacement, that's your overall change in position, is zero. Why? Because you ended up exactly where you started. So, distance is just a number, what we call a scalar. But displacement includes direction, which makes it a vector. Big difference.
And you know what? This same exact logic applies to speed and velocity. Your speed is just how fast you're going. It's a scalar. Your car's speedometer, that's what it tells you. But velocity, that's speed in a specific direction. It's a vector. It's why you can have really high speed while you're just pacing back and forth in a room, but if you're not actually going anywhere, your average velocity is zero.
And all that naturally leads us to acceleration. Now, most of us think this just means speeding up, right? Hitting the gas. But in physics, it's any change in velocity. And that means speeding up is acceleration, but so is slowing down. And get this, even turning a corner at a constant speed counts as acceleration, just because you're changing your direction. Okay, so we've covered how to describe motion. Now for the really fun part, figuring out what causes it. And for that, we have to enter the world of Sir Isaac Newton and his 3 foundational laws. This is the why behind everything we've just talked about. The star of Newton's whole show is force. A force is just a push or a pull. That's it. It's the thing that's needed to make an object change what it's doing and start to accelerate. You could say it's the official agent of change in the universe of motion. So here are the 3 laws boiled down. First, inertia. Basically, stuff likes to keep doing what it's already doing. Second, the math behind it. Force, mass, and acceleration are all linked. And third, action-reaction. You can't have one without the other. Forces always come in pairs. You can't push on a wall without that wall pushing right back on you. Let's just take a second to focus on that second law. Force equals mass times acceleration. F equals ma. This simple, incredibly elegant equation is the absolute key. It tells us that the heavier something is, the more mass it has, the more force you're going to need to get it moving. It's really the mathematical heart of all classical mechanics. All right, let's bring these big ideas down to earth for a minute. In some perfect imaginary vacuum, Newton's laws are pretty straightforward. But here in the real world, we've got to deal with things like friction and concepts like momentum that are always part of the equation. Okay, so friction. It's the force that always pushes back against motion, and it comes in 2 main flavors. First, you've got static friction. That's the stuck friction you have to overcome just to get something to budge, and it's almost always stronger than kinetic friction, which is the resistance you feel once the object is already sliding. This is exactly why it takes a huge shove to get a heavy couch moving, but a lot less effort to keep it sliding across the floor. Next up, let's talk about momentum, or as I like to call it, mass in motion. It's just an object's mass multiplied by its velocity. But here's the really critical part. It's a conserved quantity. That means in a closed system, where no outside forces are messing with things, the total amount of momentum can't change. It can get transferred between objects, like when billiard balls crash into each other, but the total amount you had before the collision is the exact same amount you have after. Now let's shift gears from forces to what I think of as the accounting system of the universe, energy. If you want to make something move or change it in any way, there's a cost, and that cost is always paid in the currency of energy. So in physics, the word work has a very specific meaning.
Work is the transfer of energy that happens when you apply a force and it moves something over a distance. So if you push against a solid brick wall with all your might for an hour, if that wall doesn't move, you've actually done zero work. I'm sorry, no matter how tired you feel. The force has to actually cause some displacement.
One of the big forms of energy is potential energy. This is basically stored energy, the energy of possibility. Think about a ball held high up in the air. It has gravitational potential energy. It's not doing anything yet, but it has the potential to, just because of where it is.
And of course, the second you let that ball go, its potential energy starts converting into kinetic energy. That's the energy of pure movement. As it falls, its height goes down, so its potential energy drops. But its speed goes up, so its kinetic energy rises. It's a trade-off.
And that trade-off is the absolute heart of the law of conservation of energy. In a closed system, you can't create or destroy energy, you can only change its form. Potential and kinetic energy are really just two sides of the same coin, and the total amount in the pot always stays exactly the same.
So now we have all the pieces of the puzzle. We know about motion, we know about forces, and we know about energy. In this last section, we finally get to the payoff. How do we use all this incredible understanding to actually manipulate our world and, make work easier for ourselves?
Let's start with one of the oldest and most powerful tools ever invented, the lever. A lever is really just a rigid bar that pivots around a fixed point we call the fulcrum. By applying a force, our effort, at one point, we can move a heavy object, the load, at another. And the magic behind all this is something called mechanical advantage.
First-class levers are the classic example you think of, like a seesaw. The fulcrum, the pivot point, is right in the middle, between where you push and what you're trying to lift. By pushing down on one side far from the fulcrum, you can lift a much heavier load on the other side with way less effort. It's a force multiplier.
Now in a second-class lever, the load is in the middle. A perfect example is a wheelbarrow. The wheel is the fulcrum, the stuff you're carrying is the load in the middle, and you provide the effort by lifting the handles. These levers are basically designed to be force multipliers. They always make it easier to lift heavy things.
And finally, we have the third-class lever, which, well, it might seem a little backwards at first. Here, you actually have to apply more force than the load itself. So why on earth would you use one? The payoff isn't force, it's range and speed of motion. Your own arm is a perfect example. A tiny contraction of your bicep muscle results in a huge, fast movement of your hand. That's the trade-off.
So there you have it. We've gone from just describing motion all the way to using these principles to build powerful tools. And the crazy thing is, the very same rule, F equals ma, that guides a massive planet in its orbit is the exact same one that lets a simple lever lift a heavy rock. It really makes you wonder, what other fundamental, unseen rules are out there, governing our world, just hiding in plain sight?